Hi everyone, my name is Fakhri Zahedy and I'm a postdoc at the Carnegie Observatories. I would like to share with you our recent discovery of multiphase gas in the vicinity of an intermediate redshift massive elliptical galaxy. This work takes advantage of a gravitationally lensed quasar system in order to probe gas at small distances from the foreground massive elliptical lensing galaxy. The scientific questions that we were interested in is, why do massive red and dead galaxies still host significant amounts of cool gas despite being quiescent? Our object is the lensing galaxy of HEO 47-1756. This is a massive elliptical galaxy at redshift of about 0.4 with a total stellar mass of 10 to the 11 times solar. This galaxy is responsible for doubly lensing a background quasar, with each lens image probing the galaxy at projected distance of 1 to twice half-light radii, or between 4 and 5 kiloparsec. In a previous study, we discovered two ultra-strong magnesium-2 absorbers along both lens sidelines, probing opposite sides of the lens galaxy. The gas has been highly enriched in iron relative to alpha elements like magnesium, to higher than solar level. This is rarely observed in the general absorber population and demonstrates that the gas has been highly enriched by type ionized supernova. When we later obtained UV spectroscopic observations of the lens sidelines with Hubble, we found that the magnesium-2 absorbers are also associated with high columns of neutral hydrogen. We find high H1 columns of between 19.7 to 19.8 in log along both sidelines, here probing opposite sides of the lens. I am showing you here the damped Lyman alpha absorption profiles we found along sideline A. The similarly high NH1 seen along both sidelines indicate an extended distribution of cool gas on 10 kiloparsec scale in this massive elliptical. Using new UV spectra of sideline A taken with COS, we have detected numerous absorption transitions from molecular hydrogen associated with the lens. These transitions originate from the ground state of H2 at various rotational levels, with some examples shown here on the left. The H2 absorption line is consistent in velocity with the strongest kinematic component of the low ions, which indicate their likely association. We perform a careful absorption analysis via void profile fitting and determine a total H2 column density of 17.8 in log. This implies an H2 mass fraction of between 2 and 5%. The observed H2 fraction can be contrasted to the lack of H2 detection in the other sideline, which constrains the H2 fraction to less than 0.1%. The stark difference in H2 fraction between these two sidelines suggests that unlike the spatially extended H1 and low ions, the distribution of molecular gas is highly clumpy and patchy on KPC scales. I have one more phase of the gas to tell you about. We also see a lot of absorption from highly ionized O6 in this system. You can see the O6 absorption profile here on the top panel. We also detect N5. The total column densities of these highly ionized species place them as among the strongest ever detected along external galaxies. The highly ionized gas has a kinematic structure distinct from that of the low ions, indicating that they arise in distinct and different gas phases. This is really exciting because really strong O6 gas like this indicates an abundance of transitional temperature gas in the galaxy. O6 is a dominant coolant near the peak of the cooling curve, so if left to itself, the gas would cool down relatively quickly. Now, if the gas we observe here is doing just that, we would infer a mass flow rate into the cool ISM of around 1 solar mass per year. Now, we don't detect star formation rate anywhere near that level in this galaxy. We have constrained the star formation rate to less than 0.1 solar mass per year. So what this suggests is that most of the cooling gas has to be reheated and returned to the hot halo. That implies a heating rate of between 1 to 3 times 10 to the 48 ergs per year within the galaxy itself. Based on this number, we find that a continuous heating from evolved stellar populations like type ionized supernova may suffice to provide the necessary amount of heating even in the absence of strong feedback from an AGN. So this case study provides a plausible explanation for why massive ellipticals like this one can maintain its long-term lack of star formation despite still having a lot of gas in their surroundings. To read more about our results, check out our paper at the link in the video description. I'm also happy to discuss our findings with you further throughout the rest of the workshop. Thank you for watching.